Okay, so in this video, we're going to talk about the universal logic gates. So this is two of our gates that we can use to build other logic functions. So we talked about this a little bit when we talked about inverting inputs and outputs. But what's considered to be universal gates is just two of our gates that's commonly used. So the advantage of this is to be able to only have one type of chip. And so we don't have to have a bunch of different types of chips on our circuit board to let us build what we need by using less chips, because we can use just one type of IC. Alright, so the universal gates, that is the NAND and the NOR. Okay, that's what we consider to be our universal logic gate. So we can use these to create any type of logic we want. Okay, so we can get AND OR, NAND NOR, obviously because of what they are. We can get a NOT function and even our exclusive gates with this. Alright, so to help us understand that, again, using this chart that we talked about with inverting inputs and outputs to find what we need. Okay, so this will help us to determine whether we need to invert the inputs to a NAND or the outputs to the NAND, or both. And then the same thing for the NOR gate. Alright, so we can create a inverting function by tying the inputs together. Okay, so for a NAND, if I tie the inputs together, that gives me a inverter function. And the same thing goes for the NOR gate. If I take the NOR and tie the inputs together, that gives me a NOT function. Alright, so from that I can build all of the other types of logic functions with that. So creating inverters by tying the inputs together of NAND and NOR gates, I can get the other logical operations. Okay, so first we're going to look at how to create those logic functions, and then we're going to actually apply it to a circuit. So one other thing I'll mention here too is that anywhere we end up with double inverting functions, we can cancel out, because the output of the two will be what the original input is to the circuit. So that's how we can begin to simplify the circuits, by eliminating double invert functions. Alright, so here we're going to draw out the equivalents. So here I'm only doing NANDs. We can do this process for the NOR gates as well, so you can see the notes that gives more details on this. So I'm only going to do, for this video, the NAND. Alright, so to create a inverting function for a NAND, again, all I have to do here is tie in the inputs. Okay, so that's my NAND gate. I'll draw my inputs here, and if I just take and tie the two inputs together, that creates a NOT function, because essentially there's only one input and one output. So this works because if I put in a low, remember with a NAND any low gives a high, so a 0 is going to give me a 1. If I put in a 1, that's going to automatically put in two 1s, and that's going to give me a 0 on the output, just like an inverter. Okay? So an AND function, if I'm using NAND gates and I want an AND function, I'm going to invert the output. Okay, so this is going to require two gates to do. So I'm going to have my first NAND. By the way, I'll put my letters here. So that will be my A and B that I'm wanting to AND together. And then I'm going to come out of this NAND and invert the output. So again, I'm using only NAND gates here. So I'm going to take a NAND function and tie the inputs together. Alright, so that's going to give me the equivalent of A times B. Okay, so it's actually A times B not again, because I've inverted the output. So the two inverting functions cancel out, so I get A times B. Alright, so for an OR function, if I got NAND, I want to OR, I invert the inputs to the NAND. So that's going to require 3 gates. Okay, so this will be to invert the inputs so that'll be A and B, and that's going to invert those signals. So I'll take the outputs of both of these NANDs into the input of another NAND. And that will give me my OR function. So that will give me A plus B. Okay, so again, this is my inverting function. So if I invert the inputs to a NAND, that will give me the equivalent of a OR function. Okay, so now the NOR. So if I have a NAND and want a NOR function, I've got to invert the inputs and the output to get a NOR. Okay, I'm going to slide this up a little bit to get room for my template. So here I need 4 gates, so I have to have 2 to invert the inputs, to the NAND function. So that will invert signal A. And then this will be used to invert signal B. And then those will combine together. And then I take the output of the third NAND and invert it to give me a NOR function. So that equals A plus B not. Okay. So that's how I can take a NAND gate and invert either the inputs and outputs by jumping inputs together and creating inverting functions to get the other operations. Okay, so that's just for the NAND. Of course, we can do the same thing for the NOR. All right, so let's look at how we can apply this. So I have an example of a combination circuit here that I'm going to use with all NAND gates. All right, so first I have A and B ANDed together. So to get an AND, I just take a NAND and invert the output. Okay, so I'm going to draw a NAND here. So I'll have A and B, and then I invert the output. So I come out of this, so that's my A and B, and that gives me my AND function for this right here. Okay, then I have C0 times D, so that's another AND function with an inverted C. Alright, so I got to create an inverter for C. So remember, I do that by jumping the inputs together. So that creates my C0, and then I AND it with D. So I'm going to take the output of this and NAND that with input D. And then I have to invert the output to make it a AND function. Okay, and then I have a NAND of E and F. So that's easy because I just use my NAND gate. So I have NAND with inputs E and F. Alright, so these two go together to a NOR. So to do a NOR, I have to invert the inputs, NAND it, and then invert the outputs. Okay, so to do a NOR, I got to invert the two inputs here. So that's my one input inverted. Here's my next one inverted. The two are NANDed. We'll put it up here. And then the output is inverted. Alright. So that creates the NOR that combines this. So all that's left now is to combine this NOR function with this AND function with an OR operation. So to do that, I have to invert the inputs. So that means this AND gets inverted. And the output of this figure out how I want to draw that. This output here gets inverted. Draw this one sideways. Okay, so those two are inverted, and then it gets NANDed together to my final output. So this is my output Z right here. Okay, so seems like a lot of work there, but this really does actually simplify the circuit, because again, we're only using one type of gate, therefore we only need one type of chip to make this happen. And then the other thing is, again, we can cancel out where we have double inverting functions. All right, so if you look, you can see some of those that we can actually take out of here. All right, so one of those would be right here. So there I have two inverters, so those could go away. I have it again right here. And I have it again right here. So these two could go away. So that eliminates 6 functions from this circuit. So when I actually build this, I can come straight off of this output to this final NAND. I can bypass this and bypass this to go to the final output. So I only actually need here 1, 2, 3, 4, 5, 6, 7 NAND functions. So there's 4 per chip, so I can build this whole thing with 2 NAND chips. Okay, so that does simplify this process. So even though it seems like a little more work to design it, it saves in having different types of chips and having to have so many chips on a circuit board. Okay, so we can do this exact same function with the NAND gate, or with the NOR gate, excuse me, as well, because NANDs and NORs are the universal gates. So hopefully this helps make sense of the NAND and NOR functions and how we can use them as universal gates. Again, if you have any questions, let me know. Thank you.